I want to say is in this structure, the fractal structure, you're going to find that on every scale, there's going to be repeats of things because there's whole numbers of tori in the bound. So there's going to be repeats in how things connect. In the whole poster of the chemistry
Oh,
constants, you can very quickly see that there's
wait a
whole
second.
repeats of a
I
connection,
think we're getting
algebraic
down to it. What?
arrangement in
Oh, the
things
electron
stamped into
volt,
nature on a
the
certain scale, on a
joule.
mass scale. Scale up in mass.
Oh, well, we actually got to the right part of the video this time. So we said it yesterday, and we'll say it again. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. So, yes, it's a wee bit later and everything, but we were trying to take care of some other stuff and things. But I said yesterday we would get into the Joule, and that's totally what we're going to do right now. So, what the heck is a Joule? I get links to everything in the doobly-doo below. The Joule. Symbol J is the unit of energy in the International System of Units. SI is equal to the amount of work done when a force of 1 Newton displaces a mass through a distance of 1 meter in the direction of the force applied. There's also the energy dissipated as heat when an electric current of 1 ampere passes through a resistance of 1 ohm for 1 second. It's named after the English physicist James Prescott Joule. So as we can see, very interesting thing here, and we learned we're just gonna focus on this for a moment because I learned some things today. So as we can see here, we got the little equation, the SI base units, definitely defined as kilograms times meters squared times seconds, so -2. So basically, you divide it all by seconds divided uh, seconds squared there. So kilograms times mass squared, divide by seconds squared. Cool. And we go over all the scales and everything like that. The one interesting thing is, when you're looking at the equivalent, yes, they have all the big joules, the little joules, and the different quantities and everything. The thing that stuck out in my mind here is I do remember not all that long ago, Rick had pointed out in a comic section, um, the relationship perhaps between 10 to the -7, which happens to be the Planck mass times the Planck length, all divided by the Planck charge squared, and then 10 to the 7th. And then I saw this. 1 joule is equal to exactly 10 to the 7 ergs. The erg, at least it's officially retired, as far as I understand, according to Wolfram Alpha, at least. But all I noticed at one point was it Professor Hassenfelder. She had tweeted out something, and they were going into different. It's usually used in cosmology still, I believe, but something about that, I'm like, ergs are totally underrated in my opinion. I think she liked it, but I'm just like, why do we have these units? I mean, again, we have these things that we use, we don't use. I would never confuse anybody. But I digress. Welcome, Whitechapel. Welcome, Fractal Automata. Thank you for joining, my friends. It's going to be pretty quick because we're basically doing the same thing we did yesterday, except we're going to add a couple of what. We're going to divide a couple of ones and then change a sign from plus to minus. That was my initial mistake. I'm like, I got everything right. I'm like, why is this off? It's like, is Dad sending me science and stuff like that when I'm actually going through? I'm like, it's not actually correct. It looks like it's, or at least to our best levels of measurement at this time. So, hey, what's going on, awesome one? Thank you for joining, my friend. But let's not bloviate. Okay, y'all know the drill and everything. We'll keep it quick and easy. So, according to our friends at NIST, this is basically essentially the Joule electron volt relationship. Because yesterday we did the electron volt, which is the little e with the big V there. And now this is the joule. So there is a relationship here. So as we can see here, the numerical value is 6.241,509,074 ... and they're setting it as exact. Why? Well, if we're using SI, we want a coherent set of units because that's how it works. A lot of these things before, they had some error bars and everything. And again, I'm not saying that the reason they had to kind of redefine is to make sure everything. Well, I mean, well, that is what they did. But let's not times 10 to the 18 electron volts. That's a lot of electron volts because you remember before, what was it? It was times 10 to the negative 19 or something. Was it joules? What did we do the other day? Hold on. Let me see. Where do we have that? Oh, I suppose I could probably just type it in. So electron volt. Boom. Oh yeah, it's basically the inverse of joules. Groovy. So that usually means we're probably going to put 1 over something. And you totally guessed right, because what we're going to do is we're going to add in, there's our little equation. Here we go. All right. So this from that video we were just going through right here. It's literally a screenshot. That's why the book should be available at some point soon. But all right, so 1 joule is basically the same equation we did yesterday, except we literally Joule 1, which is basically you square that, you get what we colloquially know as the fine structure constant. We put 1 over that, and we put 1 over the Planck charge. Because remember, yesterday, we basically had more or less the same equation, which was Joule 1, which is the first solution to the hyperbolic vortex equation, times our boundary condition, because we are using what's known as the universal binomial factorization equation. What the heck does that mean? We have a primary action. We've got stuff here, which is our boundary condition. So our primary action times our boundary condition. And then we have our terminal action here. The terminal action consists of 1 plus or minus, depending on whatever you get for your answer there. Right now, I think that's settled on basically plus. So if it ends up being negative, it's just going to be a minus sign like it is in this case. Because yesterday, it was plus this, I believe. So this terminal action is made of 1 plus the actual action itself, typically multiplied by one of the j's. This is j theta squared, which you go down to, I believe it's the third. Basically, it's that degrees radian. Oh, excuse me. Well, let's actually just go to it. We'll go hyperbolic vortex equation. Where are we? Yep. Here we go. All right. So basically, this is that Joule 1 right here. Biggin. All right. So that's point. So basically, you square that, we get basically the fine structure constant to the best of our knowledge, or at least that's the claim. I'll claim that. And then we have J3 and J4 here. We go over to our trigonometric form. I never really understood trig. Now I think I'm slowly starting to understand it. So it's the magnitude of this right here, which is essentially this distance right here from our graph here. So we got the Joule 1 and the distance from that. Cool. That ends up being that number right here. So that 2.003, yada yada. Basically just the magnitude right there. So we plug that in right back. Oh my god. We should go back to here. Oh, here we go. Okay. So we've got our J theta squared times basically the inversion boundary. This is basically where we're going to claim that there's basically an inversion going on here. And this is what we use for essentially everything in the model. It's the Planck mass times the Planck length divided by the Planck charge squared. which coincidentally happens to be 10 to the negative 7. Oh, very fascinating. And just to confirm, so we take Planck mass times the Planck length. And then, so we'll do the Planck charge, since we want to divide it. And Wolfram alpha, we just do a little up caret, and we do -2. So I'll do division for us. Cool. What do we get? Oh, it's assuming a list. We don't want a list for this. We want multiplication. Cool. Oh, look. Our friend. 1 times 10 to the negative 7 kilograms, meters, divided by seconds squared. Oh, that sounds familiar. Kilograms, meters. Oh yeah, it's in the thumbnail there. Right. Oh, I added too many things there. That's cool. That also happens to be, I believe, was it 1 ampere? Yeah. Basically, ampere's constant. Oh, very fascinating. We conjecture more about that later. Let's just jump into what we're looking for here. Okay. So here's the equation again. The links in the doobly-doo below there. So, okay. Again, this monstrosity, it's basically just what we have right here. So it's 1 over Joule 1, 1 over Joule 1, times 1 over the Planck charge, which again, we got a little, I should probably just link to the playlist and most all these things every there. So if someone wants to go through the Planck boundaries and how to geometrically derive them, they can totally look at it. And again, that's the claim. We'll see what happens. Things seem to be going pretty well. Okay. And then we have our terminal action, which is here. So that's 1 in this case. It's minus. The e, the base of natural logarithms, raised to the negative Euler-Maccheroni constant, divide by 6, times our just theta squared, times that inversion, boundary right there. As we can see, we got that 1, e raised to the minus y, divide by 6, times that number we had over there, squared, and then multiply by 10 to the negative 7 in this case. We just divide it by 10 to the 7. Gives us this number right here. Okay. So what is the number we're looking for? Where's our friend NIST? Oh no, did we already close it? What a terrible person. Sorry, these things happen. We go back to... Dun, dun, dun. Oh. Oh well. Joule NIST. Yes, we have the technology. Okay. The number we're looking for here is 6.241, 6.241, 509, 509, 074. 073. Oh, means you're off. You're off. You are correct, my friend. We are off. However, let's keep one thing in mind. According to the redefinition, we basically set a limit there. That's 4. To the best of our knowledge, our measurement, we get out to 10 decimal places here. Excuse me, 9 decimal places here. 10 significant digits. So that's a 4. We believe that is a 4 to our best level of current measurement. It's a 3. The next digit is a 6. Now, I was never really a big math guy. I just remember back in elementary school that if you're greater than a 5, you round up. So, and again, this is the claim, but I don't know, my friends. This appears to be a geometric derivation of the joule. But I think that's pretty cool. I totally learned some stuff today. Just even looking through this, I'm like, wait a second. Like you were saying, it's like the erg? Huh, that's interesting. Oh, look, the ampere? it's funny how this works. And again, maybe this is just a happy coincidence. Maybe there's no there here. I'm just saying, just happens to be a model with 2 more confirmed predictions than string theory. It's mu on G2 results and the classical electron radius after they did the redefinition. And as we get more significant digits, it can help tighten the model up. Why? Because we can. Humanity really could use a win right now, in my opinion. But that's all we got for right now. Take care of yourselves, everyone. Peace out. It's a wacky and wild world out there, but I got some hope. Why? I'm pretty sure we got this.